calculate the electrical load for a 10-story hotel, it's important to consider several factors. Firstly, let's address the general lighting and appliance load, which is calculated using NEC 220.42b. This section provides guidance on determining the minimum demand for general lighting and appliance loads and various types of occupancies. In the case of a hotel, we apply a minimum demand factor of 1.2 watts per square foot for the general lighting and appliance load. To calculate the total area of the hotel, we multiply the number of rooms per floor by the number of floors in the area per room. For instance, with 38 rooms per floor and 10 floors, and assuming 1,000 square feet per room, the total area is 380 rooms multiplied by 1,000 square feet per room, resulting in 380,000 square feet. Multiplying this total area by the minimum demand factor, we find the minimum demand for general lighting and appliances. 380,000 square feet multiplied by 1.2 watts per square foot equals 456,000 watts, or 456 kilowatts. Secondly, we will address the heating, ventilation, and air conditioning, coffee maker, and hairdryer loads. For these variable loads, applying a demand factor is crucial to account for diversity and intermittent usage. The HVAC compressor typically operates on a duty cycle of 50% due to thermostat control and cycling. Therefore, a demand factor of 0.50 can be applied to the total HVAC load. If the total heating, ventilation, and air conditioning load is 110.2 kV amps, multiplying this by the demand factor of 0.50 gives a demand of 55.1 kV amps. For coffee makers and hairdryers, a low duty cycle is expected, typically around 25%, since not all rooms will have these appliances in use simultaneously. Applying a demand factor of 0.25 to the total load of coffee makers and hairdryers provides a more realistic estimate of their contribution to the overall demand. If the combined load of coffee makers and hairdryers is 110.2 kV amps, multiplying this by the demand factor of 0.25 results in a demand of 27.6 kV amps. Thirdly, to determine the total demand, we sum the demands of all loads. This includes the general lighting and appliance load, the heating, ventilation, and air conditioning compressor load, and the coffee maker and hairdryer load. In our example, the general lighting and appliance load is 456 kilowatts, the heating, ventilation, and air conditioning compressor load is 55.1 kV amps, and the coffee maker and hairdryer load is 27.6 kV amps. Adding these together, 456 kilowatts plus 55.1 kV amps plus 27.6 kV amps gives a total demand of 538.7 kV amps, assuming the power factor is close to 1. To accurately calculate the total demand, it's important to convert all loads to the same units, typically kilovolt amps. This involves considering the power factor of each load, which represents the ratio of real power to apparent power. For purely resistive loads, the power factor is 1, meaning that the real power in kilowatts is equal to the apparent power in kilovolt amps. However, for inductive loads like motors, the power factor is less than 1, indicating that the apparent power is greater than the real power. To convert kilowatts to kilovolt amps, divide the kilowatt value by the power factor. In our example, if we assume a power factor of 0.85 for the heating, ventilation, and air conditioning compressor load, we would divide 55.1 kV amps by 0.85 to get the equivalent kilowatt value. Similarly, if we assume a power factor of 0.9 for the coffee maker and hairdryer load, we would divide 27.6 kV amps by 0.9 to get the equivalent kilowatt value. Once all loads are converted to the same units, we can add them together to get the total demand. In addition to these calculations, it's important to consider several additional factors. Firstly, confirm the diversity factor assumptions with the owner or building operator. Diversity factors are based on historical data and expected usage patterns, so it's important to ensure that these assumptions are still valid. Secondly, consider the impact of future upgrades or changes to the equipment and loads. The electrical system should be designed to accommodate future growth and changes, so it's important to factor in potential increases in demand. Thirdly, allow for some additional capacity for growth and flexibility. It's always a good idea to have some extra capacity in the electrical system to accommodate unexpected loads or changes in usage patterns. In summary, calculating the electrical load for a hotel involves considering general lighting, HVAC, and appliance loads. Apply demand factors to HVAC, coffee makers, and hair dryers due to intermittent use. Convert all loads to the same units, typically kilovolt amps, taking into account the power factor of each load. Calculate the total demand by combining all loads, and consider additional factors such as diversity factor assumptions, future upgrades, and the need for additional capacity. By following these steps, you can ensure that the electrical system is properly sized and designed to meet the needs of the hotel. These calculations help ensure the electrical system is adequate for the hotel's needs while accounting for realistic usage patterns. The NEC provides guidelines, but real-world application requires informed judgment and knowledge of the building's operational characteristics. Remember to consult with qualified electrical engineers and adhere to local codes and regulations for a safe and compliant electrical design.